otherwise known as dynamic watermarking. So I'd like to introduce you to Dr. Jaewon Kim, a research scientist at Texas A&M Global Cyber Research Institute. He's also a former postdoctoral associate at MIT's Laboratory for Information and Decision Systems, otherwise known as LIDS, and also has expertise in cyber physical systems, unmanned vehicle systems, and resilient real-time network architectures. So again, thanks for joining, and I will turn it over to Dr. Kim.
Thank you for the introduction. Howdy. Yeah, my name is Jaewon Kim. Today I'm going to talk about cybersecurity of network CPS. And one of the methodology I developed is called dynamic watermarking, which is general purpose proactive cyber attack defense methodology. And I will introduce a little bit of theory first, and then I will show some application of dynamic watermarking. Okay. And next. This is just my introduction. I can skip. Okay. So cyber physical system. What are they? So cyber physical systems is called CPS. It is next generation of engineered system in which computing, communication, and control technologies are tightly integrated. So what does that mean? Traditionally, internet was like, you can send messages to me, and I can send messages to you, and you can check my webpage, I can check your webpage. What is this? All of these are transactions of computer bits, right? But in CPS, those computer bits affect the real world. So basically, you can make something happen in the real world. I can also say these are network control system where multiple network computing nodes and diverse heterogeneous intelligent agents interact with physical world in real time, this is CPS. Okay, let me show you illustration for better understanding. CPS is tight interconnection of physical systems, such as plants, processes, and systems, and cyber components performing a computation connected by network, potentially network. So this is the picture of my lab when I was a student. So I had some ground vehicles and aerial vehicles and some power system plants and process control plant, and I connected over the network. And there is a cyber layer and physical layer. I will explain soon. Okay, and then there are many systems are cyber physical system. So for example, autonomous vehicle, chemical process control systems, UAV, and solar PV power plants. Many systems are CPS. So all of the pictures are my test bed. Okay, so let me briefly introduce about my lab, which is called CPS lab. So I installed a bunch of cameras in the high frame, which is called Beacon system, to capture the images. And then there are two computers for vision processing, which is to finding a location of the vehicle. And then there are a bunch of laptops connected over the network, which is low-level controller, which can decide next control input, such as steering angle or velocity. And then there is a high-level controller for waypoint generation for each vehicle. And then there are ground vehicle and air vehicle, and low-level car controller, low-level drone controller, and low-level process control system controller can control this. And there is a safety net for safety protocol, and two big drones for the outdoor. This is the lab setup. So now I want to talk about the security of CPS and why it is important. Okay, so many societally critical systems are being networked. So such as smart grid, autonomous vehicle, UAV transportation, and chemical process control systems, and water treatment facility, and so on and so on. So many systems are CPS. So they are safety and economy critical. So malfunctioning can cause considerable physical damages and economic damages. So actually, there have been many attacks in the real world. So those are many attacks happen in the real world. So for example, Stuxnet, Ukraine power grid, Shaman malware, and Ohio nuclear plant. the thing is, the problem is, even after many decades, we still cannot secure internet and operating system. So that's why you are keep getting this security update every day, patching. So how can we possibly secure CPS? That's my question. Okay, let me introduce some real-world attack on CPS. First, Stuxnet. Stuxnet actually targeted SCADA systems for advisory, control, and data acquisition system. It was designed to cause critical damage to Iranian centrifuge, which is used to enrich uranium. And next one is Ukraine power grid attack, which is cyber-induced power outage. The attacker used a malware called Black Energy to compromise the information system of 3 energy distribution companies. And the next one is Ohio nuclear plant. The attacker used a malware called Slammerworm, which penetrates a private computer network, which disabled a safety monitoring system for a few hours. And then the Shaman malware is targeted oil and gas company, and they paralyzed their business network for several months. So that's why security of CPS is very important. And here, this is a timeline of the attacks. Many attacks happening every day, even now. So that's why we have to find a way to defend those attacks or detect attack and identify which component is under attack. Then we can develop some mitigation technologies. And here is the recent post from FBI Cyber Division. They announced the public service warning that Russian FSB cyber actors are exploiting simple network management protocol, which is called SNMP, and the live networking devices running on unpatched vulnerabilities in Cisco Smart Install SMI to target entities across the critical infrastructure sectors. So attackers are targeting our critical infrastructures. So we need to develop some technology to detect those attacks. Okay? So if you are interested, please check it. Okay, then abstraction of network CPS. Overall system has physical system, which can be autonomous vehicle, UAV, power system, process control, and so on and so on. And there are a bunch of actuators, bunch of sensors, and they are connected over the routers, so multiple routers, and then multiple computational nodes, multiple information fusion nodes. They are connected over the network, which can be wired, which can be wireless. And then, however, some of the nodes could be compromised, could be malicious. So how do we secure the overall network CPS? So network CPS are vulnerable to potential attacks where malicious agents compromise the sensors or the network carrying the sensor measurement. Okay? And some of the network nodes may be compromised or malicious. We say sensor is compromised if information from a sensor is compromised. Okay? Then how do we secure overall CPS when some sensors may be malicious? Okay? Okay, so let me give you some illustration with malicious sensors within the CPS. Here we have a dynamical systems. We have sensors this side, we have actuator this side. During the normal operation, I denoted GT equal to reported measurement from the sensor, and YT is actual value from the actual value of the system. So if the sensor is honest, the ZT exactly equal to YT. But some sensors could be malicious because of attacks. Then they can report first measurement to the controller. It can cause critical damage to the system, such as Stuxnet. Okay, what is the solution to defend these kind of attacks? So they have so many solutions, but I'm going to talk about my solution, which is called dynamic watermarking. So I will introduce how to implement dynamic watermarking to make cyber secure operation. Okay. So here is the picture. How can we apply dynamic watermarking? So here is the sensors, here is the actuators, and control input UT depends on ZT. So that's why if some sensor is malicious, then attacker can compromise the system. Attacker can break the system. So to defend this, I actually injected very, very small excitation signals, which is ET. So instead of just injecting UT, we are injecting small watermark ET. So actual input will be UT plus ET. It's like here to the system. And then why it is called watermark? So because it is indelible, like a watermark on a paper or watermark on a $100 bill. It cannot be removed from the sensor measurement. It is overlapped on the sensor measurement. And then once we inject watermark, it goes through all the way through the system and come back appropriately transformed to the actuator. Then attack detector at the actuator side can check if the reported measurements are appropriately correlate with the random excitation signal ET, which is watermark. So I will give you the simple example, which is single input, single output system. So here we have a system equation, XD plus 1 equal to AX plus BU plus W, which is system noise. And XD is a system state, which can be velocity, position, something like that. And UT is our control input of the system, which is normal equation. And I am injecting small noise, ET, small excitation signal. So our new U will be UT plus ET. And then ET is following the distribution of normal distribution, mean zero and variance sigma E square in this case. And then the closed loop system will be rewritten like this, AX plus BU plus B plus W T plus 1. And then I can rearrange this equation with two different ways. One with watermark at on the left-hand side, and another one is the watermark at the right-hand side. I can use these two equations for test 1 and test 2. So which is like this. So first equation is test 1, second equation is test 2. So during the normal operation, in the absence of the attack, so the test 1 left-hand side should be equal to system noise. And test 2 left-hand side should be equal to system noise plus watermark variance, which you injected, right? So if either test fails, then there is a malicious information within the system. Then after we detect, the system should go into safety mode, which can be halted, which can be rebooted, which can be manual operation. So for example, you cannot stop the drone in the middle of the air, so you have to change it to human pilot or the safe landing controller. So but if it is a process control system, once you detect attack, you have to drain all of the waters, drain all of the toxic chemicals, something like that. And then there is a trade-off for setting detection threshold. So if we set high threshold setup, it will result in more miss alarms. If we set low threshold setup, it will result in more false alarms. So that's why we have to carefully test it for implementation of this dynamic watermarking. So this dynamic watermarking method has been experimentally tested on process control system testbed, which is coupled water tank, and mechanical system, which is helicopter testbed, and vehicular system, autonomous car system, and then power system with power electronics, which is grid-tied inverter. And then the benefit of this dynamic watermarking methodology is a general purpose proactive defense methodology for defending control system against any potential attacks. So why do we need experiment? Some people say, oh, we can do everything in simulation. No, I say no. So why we need? Because this dynamic watermarking methodology is fundamentally based on stochastic consideration, not deterministic. So for example, this is one of the picture from the chemical process control system testbed example. There's a froth in the water flow into the bottom tank, which constitutes noise, which is quite substantial. But there's no mathematical model for this. So, and also the critical issue is, does our tiny watermark signal that is superimposed to the system can survive within this? And also, how small can watermark be? So therefore, we need to do experiment, not validate by simulation. And also, there are several reasons for why we need experiment. The first one, dynamic watermarking methodology, calls for active injecting noise into the system. So we have to check our noise is not breaking the system. If you inject too much noise, you are breaking the system. So that's why we have to do some experiment and make sure this noise is not too much. And then second reason is the lower the variance of the signal employed, the longer potentially is the time to detect an attack. So what is the trade-off between miss alarms and false alarm? This can be only done by experiment. And what is the detection delay? And also this is designed to be a general purpose method, so we have to test it. So that's why we need experimentation other than simulation only. So we should do simulation, experimentation, both of them. Okay. Okay. So now I'm going to show some examples of application of dynamic watermarking. The first one is the process control system testbed application, which is coupled water tank. So there is a water pump feeds into the tank 1, and input water flow will go to the tank 1, and tank 1 will feed tank 2. So we are controlling level 2, and level 1 and level 2 is connected. And then the controller is designed to regulate or track the water level in tank 2. So the water level is measured by pressure sensor at the bottom of each tank. So this is a prototypical process control system. So let me show you. And then this is very simple testbed, the single input and two output. The input is the pump voltage, and you can control. And then output is level 1 in the tank 1 and level 2 in tank 2. So two output, one input. And then before I inject any watermark, I tested with a very different watermark. So here is the input voltage and with different watermark level, and here is the sensor level measurement from the sensor, water level sensor. Then I can decide this is no watermark, variance 1, variance 2, and this is all overlap. And then I decided, oh, dynamic watermarking does not cause any significant performance degradation, so you have to check if you want to apply. And then here is the, can you go back? And here is the video. So initially, initiating the plant, and then we set the reference at 15 centimeters here and see a lot of froth, which is noise. And in the absence of the attack, it's working properly. Okay, now let's attack on the sensor. And malicious sensor can cause overflow, but system doesn't know without any defense methodology like this. So we implemented dynamic watermarking for monitoring in real time, so which has two tests. So test 1 and test 2 are keep monitoring the behavior. And once the attack is detected, we are continue the process, and then we stop all the tanks and drain all of the water. And then here is the result. We can detect any attack within the 20 milliseconds. You can read this paper. This is my paper in IFAC 2020. Okay, next one, I'm going to introduce about dynamic watermarking methodology application in power system. So defending against the potential attacks on grid-type solar PV power distribution system. So PV dominant distribution grids are also CPS, and attackers can compromise the system by manipulating device at the grid edge. How to defend PV dominant distribution grid against potential attacks. And then here is our lab setup. So we connected two DC source as mimicking solar, and then two inverters are connected to the same grid. So we have AC source as mimicking the AC grid. Okay, next. And then first, we attacked on inverter 1, which is harmonics distortion attack. So here is the attack time. You can see before the attack, there is a normal operation, and after the attack, you can see a little bit harmonic distortion, which is grid current in inverter 1, and yellow is grid current in inverter 2, and the voltage inverter 1, voltage inverter 2. Once we attack on inverter 1, the dynamic watermarking test 1 and 2 at the inverter 1 shows only jump. But dynamic watermarking test 1 and 2 at the inverter 2 just showing normal. And next, we attack on the inverter 2, little bit decrease the current, 100% to 90%. So you cannot tell before attack and after attack, but system can detect. So here, dynamic watermarking test 1 and 2 at the inverter 2 can show the jump, and then this means something is going on, something is under attack in inverter 2. So our dynamic watermarking is not only can detect attack, and also we can identify attack location. This is very important. So in this example, two inverters are connected to the same grid. So think about like this. If hundreds of inverters, like home 1, home 2, home 3 to home 100 is connected to the same grid. So if somebody is under attack home 3, 4, 5, then we should not shut down everything. We should identify which home is under attack, which component within the system is under attack, then isolate that compromised component only. So both simulation and experimental validation on two inverter connected system, we have determined we can not only detect attacks, we can identify attack location. And then after we done with this lab experiment, we visited Central Energy Solar Farm in Evansville. They invited us. They were actually in this project, and this project is DOE sponsored project, and they were in the project as an industry partner. They really liked it, and they invited us to their solar farm. And they have 3 solar farms basically. The one is called Oak Hill Solar Farm, has 8,000 solar panel and 2.5 megawatt solar inverter and 2.7 megawatt DC solar field. And Borkman has the energy storage systems, which is 4.5 megawatt hour. And these 2 are basically test beds to test anything. And they also have Troy Solar Farm. They have 150,000 solar panels and tracking system to keep track of solar to maximize their generation, which can provide 50 megawatts. And then here is the simple diagram to how to implement the watermark on their system. Because in the difference between the lab scale test bed and commercial test bed is lab scale you can access everything, including controller, control input, everything. But there, they just buy the company inverter, like SMA, Enphase, something like that, Mitsubishi, something like that. We don't have access to the control. So according to the theory, we should inject watermark on the control input U. So, but here in this case, we cannot. So that's why I was thinking how to make it happen. So, but only access point we can do is the input of the inverter, which is solar DC link. So in their case, they are keep monitoring the irradiance. Irradiance is the watts per square meters. So we injected watermark here, and then it appear on the sensor level. So inverter sensors and transformer sensor. And same for ESS. So we can inject battery. This is also DC. Solar is also DC. So we can inject watermark here, and then we can monitor here, 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 here. So all of the sensor measurements are attack points. Okay, and let me explain a little bit about overcoming the requirement to know the system model. Because dynamic watermarking, as you can see in the equation, in the test 1 and test 2, you have to know somehow the model equation. But in real world, you cannot, right? You don't have any models. So that's why, generally, an accurate model of the system is unknown because of non-linearity of the system, as well as the complexity of the connected power grid. So therefore, proper system identification method is critical, essential, not only for controlling the system, but also for analyzing the effect of external disturbances and possible fault in the system. So that's why we develop many system identification methods, which can be offline, which can be online. Here is one of the identification model, which is RMX model, autoregressive moving average with exogenous input. So alpha 0, alpha 1 to alpha n, beta 0, beta 1 to beta n. We are actually fitting this model and deciding AN matrix is all of the alpha coefficients, and BN matrix is all of the beta coefficients. Okay, here is a simple example. If we want to identify module 1, so let's make it simple. The U1 is the input of the module 1, and Y1 is the output of the module 1. So you can write the equation like this. And then for module 2 and module 3, same. So we can estimate actually. So that's why I put hat, not actual measurement. Y1 hat is almost close to Y1, and Y2 and Y3 hat. Okay, and based on this, I am basically making a cyber secure and resilient defense framework for any kinds of cyber physical systems. So for example, here is all of the sensor measurement, and here is the time axis. And some people came into the network and they record and replay at some time. Human operator cannot detect this kind of thing because it's still within the boundary. So upper bound, lower bound is still same. But I have the dynamic watermarking attack detector, can say no attack and attack detected, which can be 0 flag and number 1. So 0 means no attack, 1 means attack is detected. And once we detect attack, we can fast identification of attack location, which is localization. Oh, there is a car 1, car 3, car 4 is under attack within the system, so we have to isolate those components only. Then attack mitigation procedure has 3 levels. So device level, we can safely shut down the device, and system level, we can actually keep control even under attack using the secure corrective control methodology. And then there's another network level mitigation, which is zero trust micro-segmentation based network traffic control policy. We can actually design network control policy. Once attack is detected, that component is compromised or malicious, then all of the inbound traffic, outbound traffic from the compromised component should be blocked or should be checked. So we can design those kind of things. So that's the network level mitigation. And then here is my last slide. And I couldn't show all of the examples. I implemented dynamic watermarking to many systems, including autonomous vehicles and drones and power system and the chemical process control system. So if you want to check more result of this, you can check my Google Scholar, and this is my LinkedIn profile. Thank you for attending my talk. Any questions? Okay. First. Can I get mic for the audience?
So my question to you is it possible for the system that's creating the watermark code to become compromised itself? And how would you protect that?
No, actually the dynamic watermarking is injected by the owner, so operator. And then we are injecting small noise. We are deciding the random value is following some distribution. we can even let them know I'm choosing this value from this distribution, but those random value is selection of the random value is keep changing every control sampling time. For example, the inverter system is microsecond scale. They keep changing microsecond scale. So attacker cannot guess which the actual key value is they keep changing, but even if they know the distribution, they cannot guess.
And what is generating the watermark?
The simplest one is generating random number and injecting the random number onto the sensor measurement, which can be voltage sensor measurement, like position sensor measurement. Instead of reporting 0, reporting 0.001, 0.001, something like that.
Gotcha. Thank you.
I got two questions.
Okay.
One is, I'm assuming every CPS is going to be sensitive to different levels of noise input. How do you calculate the amplitude that is allowable in a system, or is experimentation the only way?
System noise?
Yes.
So first, what I did in many examples, first I am keep checking the normal operations upper bound of the noise level and lower bound of the noise level, and then decide this boundary is normal operation, lower bound and upper bound. Then I am slowly injecting the watermark and check if it is too much or if it's not too much. So that's why I said we need experimentation instead of simulation, because simulation you don't know the noise.
Right.
Yeah. And next question.
The other question was, what kind of compute is necessary, both for I'm assuming you need some sort of cryptographically secure number generation to go for the input, and then you need something to do the calculation and the output. What kind of compute is necessary to practically implement this?
Yes. So the practical implementation point, it depends. So if the robot has low computational power, like if you're using Raspberry Pi, you cannot do high computation on board, right? So for that, you can just generate random number, and that random number is following some distribution. Like maybe very simplest one is the Gaussian distribution. Just mean 0, and you can set some variance and keep injecting. And if you have high performance, you can generate more using GPU. Thank you. And also you need to think about the network delay as well. So if the sensor measurement is delayed to the controller, itself also attack. So you are feeding the one step before measurement to the controller. The controller will decide wrong decision to the plant, just keep messing up. So network delay is also another consideration. Another question? Okay. Thank you for coming to my talk, and if you have any questions, please email me or send me a LinkedIn message, and I will answer your question. Thank you.